All right, optimization. Um, Optimization is simply finding the max and min of a function. But in order to do that, we have to actually determine a function. So that's mainly what we're going to be doing here. Remember, to find the max or min, we take the derivative and the second derivative of the function. We set the derivative equal to 0 and solve, and then we test our critical numbers in the second derivative to determine whether that's, remember, if it's a negative, if the second derivative is negative, that means it's curving downwards. So we have a max. And if the second derivative is positive, then that means it's curving upwards, so we have a min, right? So that's the basic test for finding a max or a min. So now let's take a look at some example problems. With all of these, if you think you can do them on your own, just go ahead and try them and then just check back with my results. But you may want to follow through the process on at least one of these before you try on your own. First one, a box company has a rectangular sheets of cardboard that are 20 by 30. So it looks like this is 20 by 30. I'm going to go ahead and write that down. If they were to cut out squares in the corner to make an open top box, what size should the squares be to maximize the volume of the box? So see, they're going to cut out these corners and they're going to fold up the sides, and it's going to create a box. So we want to make the maximum volume. To do that, we need to know what size squares to cut out. So before we move on, oh, and they are all asking what would the dimensions of the box be. So 2 questions to answer here. So before we move on, I just want to point out, so these, we don't know what size these squares are, but we could mark this as so. And because we're marking that, we could actually figure out that this distance here is going to be 30 minus the distance of these boxes, which would be 2 of them, so that'd be 2x. And in the same way here, this distance would be 20 minus 2x. Okay, so I know my writing's a little bit weird here. So we got 20 minus 2x and 30 minus 2x. And then when we fold it up, the height would be x. Maybe this is a better place to write it. 20 minus 2x here, and 30 minus 2x here. So now we have variable expressions for all 3 lengths of our box, so we can actually write the formula for volume. So let's go ahead and do that over here. Volume equals, and volume typically equals length times width times height. So in this situation, the length is 30 minus 2x. The width is 20 minus 2x, and the height is x. Well, since I know that I'm going to be taking the derivative later, I'd rather take the derivative of a polynomial function that's in standard form rather than in factored form. It's a little bit easier. So let's go ahead and factor this out. So first I would get 600, I'm just doing FOIL. So I'd get 600, and then 30 times negative 2 is negative 60 x, and then 20 times negative 2 is negative 100, or negative 40x, and then the last would be negative 2 times negative 2 is positive 4x squared. And then remember, this whole thing is times by x, so I'm going to distribute that to every term. So I'm going to go ahead and put it in standard form too, so I'm going to move this to the front. So that gives me 4x cubed. These guys can be combined to make negative 100x, so I'm going to say negative 100x squared, and then finally plus 600x. So here's my formula for the volume of the rectangle here. And remember, I'm trying to find the maximum volume of the box. So to do that, I'm going to take the derivative. So let's go ahead and take the derivative of this guy. So the derivative would equal 12x squared minus 200x plus 600. Okay, let's just review to find the max. Remember, we take the derivative and the second derivative function. So, and then we're going to set the derivative equal to 0 and solve. So let's go ahead and find the second derivative as well. This would be 24x minus 200. Okay, so they want us to take the first derivative and set it equal to 0, so let's go ahead and do that. So I would say 12x squared minus 200x plus 600 equals 0. I think that I could simplify that quite a bit. Looks like I could take a 4 out of all of these values, so I'm going to go ahead and divide both sides by 4. When I do that, I get, I'll do it in blue, 3x squared minus 50x plus 150 equals 0. Pretty sure this isn't factorable, so we're going to have to use the quadratic equation to solve this. So quadratic formula says negative b, which would be positive 50, plus or minus the square root of b squared minus 4 times my a value times my c value all over 2 times my a value. Okay, so we're almost there. Just a little bit of, some algebra stuff. We're going to set this equal to 0 and solve. Then we're going to test these values in the second derivative to find out if those are maxes or mins. So let's go ahead and work this out. I got 50 plus or minus. This would be 2,500. And 4 times 3 times 150 is 1,800. So we could say 2,500 minus 1,800 all over 6. So this is 50 plus or minus the square root of 700 all over 6. And you could simplify this down. If you wanted to simplify and reduce, you'd eventually get down to 25 plus or minus 5 or at 7 over 3. And this could be equal to the decimal answer of 3.92 and 12.74. So we found our values of x. Now what I want to do real quick is I want to point out, if we were to take away 3.94 or 3.92, that would work just fine because this is 30, this is 20. I could take away 3, or take away almost 4, I'd have what, 12 here, right? If I took away 4, I'd have about 22 here. But if I took away 12.74 from each side of 20, well, I'd run out of room, right? There'd be no side left here. So that is not really a realistic value to evaluate. So the only one that we're going to look at is when x is 3.92. So we're going to check by plugging that into the second derivative. Let's see if it's a max or a min. So we want the second derivative of 3.92. That is going to be 24 times 3.92 minus 200. And all we're really looking here is whether this is going to be a negative or a positive. And this is going to be really close to 24 times 4. And that, if I was to just estimate 24 times 4, well, that's 96. So I end up with 96 minus 200. So this is a negative. That's perfect because that tells me, remember, if the second derivative is negative, that tells me that this is curving down, so therefore I have a max. So I just found the max. It's at 3.92. It's when the x equals 3.92. So the little squares that we would take out should be a length of 3.92 inches. What else does it say? Which I said the square root is to maximize the volume of the block. We got that. What would the dimensions of the box be? Well, that's easy because we have those dimensions here. We know the length is 30 minus 2 times 3.92. The width is 20 minus 2 times 3.92. And obviously the height is just going to be 3.92. So we can just quickly figure the rest of these guys out, right? 30 minus 2 times 3.92. So that's about 22.16 inches. And the width is 20 minus 2 times 3.92, and so that's 12.16 inches. And there we have all the dimensions. So we've answered this question. So just to recap, remember I came up with a formula for the volume, then I took the derivative of that function because I'm maximizing it. I also took the second derivative. I took the derivative, set it equal to 0, and solved. And I got two values, and I kind of realized that one of those values was not really probable. And then I just took the value and plugged it in to find my dimensions. So let's try another one on the next video.